Okay, welcome. This is a section on 6.2, complete graphs. So as we talked about in the last section, we talked about what a Hamilton circuit and a Hamilton path is. Today we're going to look at what a complete graph is. So let's first figure out what that means. So we'll write for me a complete graph. So a complete graph, you can simply write that it means that every vertex is joined by every other edge. So I'm going to write it like this. Every pair of vertices is joined by an edge. If definitions make sense to you, then great. For me, I'd rather see a picture than read a definition. One thing you need to know is this. I'll put a star next to this one. You need to know how to find degree. So degree of a vertex. This is for a complete graph. It's pretty simple. I'll write here D equals N minus 1. And N stands for vertices. We're going to use N in all of our equations and formulas today. So again, it's a little confusing to write a definition, so maybe it'll make sense if we draw a picture. So I'm going to draw a couple of pictures. Here's one. So that is a complete graph, K, 3, a complete graph with 3 vertices, meaning that this vertex is connected to the other two, this vertex is directly connected to the other two, and so is this vertex directly connected to the other two. Let's draw one with 4 vertices. I'm going to draw a box. So right now I have kind of a complete graph, except that this vertex is not connected to this one directly, so I'm going to connect them straight across. This vertex is not connected to this graph, so I'm going to draw it going straight across. A complete graph now with 4 vertices. Notice how the degree of every single vertex is 1 less than the number of vertices we have. For example, we have 1, 2, 3 vertices. The degree here for each of these vertices is 2. We have 4 vertices. This is not a vertex in the middle. 4 vertices. The degree of each is 3. It's always 1 less. Vertices minus 1. We'll do one more. Let's say you had a complete graph with 5 vertices. So every single vertex needs to have, now if it's a complete graph with 5 vertices, every single vertex needs to have a degree of 4. So if I drew one line connecting there, that makes 2, this makes 3, this makes 4. I need to do the same thing for all the other graphs. This edge is already connected to this vertex here by this edge, so I can draw one going straight across. Now this vertex has a degree of 2. Now it has a degree of 3. Now it has a degree of 4. This vertex has a degree of 2 already, so I connect one here to make a degree of 3, one more to make a degree of 4. And then finally, this vertex has a degree of 1, 2, 3. Add one more edge to make it a degree of 4. So that's a complete graph with 5 vertices. The K for complete, I don't know why they use a K, and then the 4 for how many vertices you have. Another formula to know is edges of a graph. So edges in a complete graph. There's a formula to know for this. I'm going to write E for edges equals N, remember that stands for vertices, times N minus 1, all divided by 2. Remember again, N stands for vertices. So if we look back up at our previous graphs, so E stands for edges. So in a complete graph with 3 vertices, 3 times 3 minus 1, 3 minus 1 is 2. So 3 times 2 is 6. 6 divided by 2 gives me 3. So that means that there should be 3 edges in this graph. There are 1, 2, 3. We'll do it one more time. This complete graph has 4 vertices. Plug in 4. 4 times 3, which is 4 minus 1. 4 times 3 is 12. Divided by 2 is 6. So we count the number of edges up here. We got 1, 2, 3, 4 on the outside, 5, 6 on the inside, 6 edges for a complete graph. So those are 2 formulas so far to learn. You can also find the number of circuits in a complete graph. So right here, circuits in a complete graph. I'll use a C for circuits. Your formula is N, remember it stands for vertices, minus 1, factorial. So let's look at those last 2 and figure out questions that may have to do with that. So let's say, for example, you were given a graph that has a certain number of edges and or vertices, and you're trying to figure out how many edges that graph would have. So let's say your graph has 6 vertices. How many edges would it have? We're going to plug in 6 for n. So I take my numbers, I plug in 6 for n. 6 times 6 minus 1, all divided by 2. 6 times 5 is 30. 30 divided by 2 gives me 15. For number of circuits in complete graph. What if you were told there were 8 vertices and asked to find how many circuits there are? So I take 8 minus 1, factorial. 8 minus 1 is 7. So the answer is 7 factorial. If you actually wrote that out, you could do it on the calculator. Remember, if you do it on the calculator, you want to hit the factorial button. So a quick recap, you're going to hit 7 first. Hit the factorial button by hitting math, which is right here on the left-hand side. Arrow over to your PRB menu. Go down to option number 4. And 7 factorial gives you 5,040. So there's 2 examples for how you figure out how many edges and circuits there are on a graph. One more term to know is a mirror image. This will be our last one. So let's write down, in this case, all of the Hamilton circuits in this graph. So we're going to draw a picture of a box, a square with A, B, C, D on the outside. We're going to make it a complete graph by drawing all 4 of those connected on the outside and then connected on the inside. Every single vertex should have a degree of 3. We should have 6 edges. That's how we know it's a complete graph. Now I want to figure out what are all of my circuits going to be. If I were to list out all my circuits, so first of all, remember, if I'm trying to figure out how many circuits are there going to be, well, if I were to plug in 4 vertices minus 1, 4 minus 1 is 3, 3 factorial is 6. I should have 6 Hamilton circuits. So when I list those 6 Hamilton circuits, you'll start to notice a pattern. So let's start with vertex A. Now let's go in order. So we'll just do A, B, C, D, and back to A. Now, what if I were to do the exact same thing, but go in the opposite direction? If I were to go in the opposite direction, I would, instead of going A, B, C, D, A, what if I were to do A, D, C, B, A? It's the same exact circuit, except it's going in a backwards order. That is the same thing as something, if you were to stand in front of your mirror and read something in the mirror, it would look like it was backwards. Same thing as if you're driving on the road and you happen to see an ambulance behind you. The word ambulance is usually written backwards so that when you see it in your rearview mirror, you can read the word ambulance. This is called a mirror image. You can write it as mirror or mirror image or mirror image circuit. Let's find another circuit. Let's start with A. Let's go to B. But this time, instead of going C first, let's go D first. Then we'll go to C, back to A. Let's do the mirror image of that circuit. So it's the same exact thing, except it's going to be backwards. So instead of looking at my graph this time, try covering up your graph and looking at just your letters. To go in reverse order, I'm going to do AC. Just go backwards. A, C. C goes to D. D goes to B. And B goes back to A. Again, there's your mirrors. All right, so I've listed all the ones that start at A and go to B. So now let's list the only one that starts at A. And this time, let's go to C. Let's go in a different order. So let's go AC, B, DA. And again, we'll list the mirror image of that, which is A, D, B, CA. And again, that's your mirror image. That is how you find edges, vertices, degrees, and how you find what's called a mirror image circuit for 6.2 complete graphs.